Hello, this is Dr. Hanaa Assil, and this is the third and last part of the questions and answers on electrochemistry. So this question says an electrochemical cell is made from the electrode systems shown. The apparatus used to measure the value of the E cell under standard conditions is shown. Which silver compound could be used as the electrolyte in the left-hand half cell? Again, I'm going to remind you, electrochemical cell is made up of two half cells. So each of these beakers is a half cell. Now, I want in the beaker on the left, I want silver ions. So they should be something that is soluble. So that would be silver nitrate, and the solutions have to have a concentration of 1 mole per decimeter cubed. Then the second part of that question says the electrolyte in the left-hand half cell is prepared using equal volumes of what? So if we have these equations and this was the half cell, now I want to make equal volumes of what for the right-hand half cell. Now the right-hand half cell has the VO2 1 positive to give VO2 positives. And we said if we have a mixture of the solutions, overall the concentration of each ion in the solution should be 1 mole per decimeter cube. But remember that you are going to take equal volumes and then add them together, and that means you're diluting each of them by half. And that means you need to prepare originally 2 mole per decimeter cubed of each of them, so that when you take equal volumes and add them together, then the overall concentration would be 1 mole per decimeter cubed for each ion. Are we paying attention? Okay. This one says, which is the equation for the overall cell reaction that we have up there? Well, we said when we write all of this, we write them so that the first one and the second one are the same as what we want. We look at the electrons. They are the same number of electrons before and after the arrow. Remember that when you invert an equation, you invert the sign of the E node. So we inverted that first equation. We inverted the sign for the standard potential, and then we add everything before and after the arrow. So overall, this is our overall cell reaction. Are we okay with all of this now? Again, if he says, what is the value of the E cell? We said we inverted that first equation, so we need to invert its electrode potential, because the electrode potentials listed are for reduction. This is oxidation, so the E of that first equation is now a minus. You add them together, then the overall E cell is plus 2 volts. What is the cell diagram? Do you remember how we drew cell diagram? How do we draw the cell diagram? We said we start with the oxidation part. So which one is the oxidation part? We start with that on the left. We're going to have silver solid to give silver plus. That is our setup in the equation. So silver solid slash silver plus, that is my first half cell with state symbols. And then we said we put in 2 lines. This indicates the salt bridge between the 2 half cells. Now, what is happening in that other half cell on the right? That is the reduction part. So we're starting with VO2 with 1 positive aqueous plus 2H plus aqueous. We don't put electrons in the cell diagram. And then we have a slash to indicate that this is one part, or the part before the arrow. Now the part after the arrow is VO with 2 positives aqueous plus water liquid. Which electrode are we using? Again, I'm reminding you. If we have a solid, then the solid is my electrode. So in the silver solid, the silver electrode is the solid. But in the other part on the right, we have only vanadium solutions or vanadium ions in solution. So we need a platinum electrode. Are we okay with this? So this is what we call the cell diagram for the cell. Again, the apparatus shown was used to measure the standard electrode potential for reduction of dichromate to chromium ions. Which material should be used for each electrode? Well, let's take a look. The one on the left, electrode 1, that is the standard hydrogen electrode. And remember that the hydrogen electrode has hydrogen gas at 100 kilopascal or 1 atmosphere. And it has a solution of what? If we're asked what is the solution is sulfuric acid, 1 mole per decimeter cubed, or 1 mole per decimeter cubed of a strong acid. Now, what is electrode 1? Remember, we have gas and solution, so the electrode 1 has to be platinum. Now, on the other half cell on the right, what do we have? We have dichromate ions, chromium 3+ ions, and that means we have a solution of ions, and that means also the electrode has to be platinum. Now, what is solution 1? Remember, we said solution 1 has to be a strong acid, and it has to be 1 mole per decimeter cubed. So we said it could be 1 mole per decimeter cubed of sulfuric acid, for example, but this is not one of my choices. So the only 1 mole per decimeter cubed of a strong acid in this case is the HCl. Solution 2 contains 14.71 grams of dichromate. Again, I'm going to remind you that if we have 14.71 grams of potassium dichromate, I can get the number of moles, mass over molecular mass. But then we want what? We want the chromate ions. So the chromate ions, 1 mole of potassium dichromate will give 1 mole of Cr2O7. So if we have 0.05 mole of K2Cr2O7, then the number of moles of the chromium 3+ must also be 0.05 moles so that they are equal concentrations. But the problem is the chromium Cr2SO4 this 1 mole of this solid will provide 2 moles of chromium 3+. And that means if I'm trying to get the number of moles of the solid, that would be half of what we require for the chromium 3+, because each mole gives twice the number of moles of chromium 3+. We need 0.05, so we need 0.025 of the solid, and then I can get the mass, so that comes out to be 17.91 grams. Are we okay with that? So if something provides twice the number of moles of the ions, please take that into consideration. Solution 2. Again, which one is solution 2? Solution 2 is the one with the dichromate. It is best acidified with what? Well, it would be best acidified with something that would not react with it. So it is acidified with sulfuric acid. The others, as chloride and bromide, may be oxidized. So we do not include an acid that can react. And we cannot include an acid that has a different chromium ion. That's as if we're adding extra chromium ions to the solution. So the acidification has to be with the correct choice out of these is sulfuric acid. The equation for a redox reaction is this, which is the correct cell diagram. Again, how do we write cell diagrams? We start on the left with oxidation. Where is oxidation? Ion 2+ to ion 3+. But then we said this is a mixture of solutions of ions, so the electrode has to be platinum. So my answer is C or D. Now, which part is the reduction? Manganate 4 MnO4 minus plus 8H plus aqueous to give Mn2 plus aqueous plus 4 water. Again, this is a mixture of ions or solutions, so my electrode on that side also is platinum. Can we see how we draw it? So it's platinum slash iron 2 plus iron 3 plus, and we said the double line in the middle indicates the salt bridge, and then the rest with a platinum electrode. Which is true of a hydrogen-oxygen fuel cell? Okay, we are required to know what is a hydrogen-oxygen fuel cell. Remember, a fuel cell is one that produces electric current by continuously providing it with reactants. So the hydrogen-oxygen fuel cell is one that uses up hydrogen and oxygen in order to give water, and during this reaction there is exchange of electrons, and that provides an electric current. So that's the hydrogen-oxygen fuel cell. Now, what is true of a hydrogen-oxygen fuel cell? I want you to note the sign of the anode and the cathode. In normal electrolytic cells or in electrolysis, we used to say that anode is positive, cathode is negative, but here they have the opposite signs. So here the anode is the negative and the cathode is the positive, and these are the kinds of reactions that happen, so that the overall reaction is hydrogen plus oxygen to give water. So which of these choices is correct? Of course, the cathode is more positive than the anode. Again, I want you to remember that the hydrogen-oxygen fuel cell may either be alkaline or acidic. So this is the equations, or these are the equations for the alkaline in presence of OH minus. So the half equation at the negative electrode, remember we said the negative electrode is the anode. This is where the hydrogen reacts to give water. A hydrogen-oxygen fuel cell is used to provide electrical energy for an electric motor in a car. The electrolyte is acidic. Now, the other one was alkaline. What if it is acidic? Well, these are the equations for the acidic fuel cell. So what is the half equation at the anode? Again, the anode is the negative, and this is where the hydrogen reacts. But in this case, because it's acidic, not alkaline, the hydrogen loses electrons and becomes H plus ions. Okay, standard electrode potentials can also be given an alternative name. The electrochemical series lists standard electrode potentials in order. Now, which of these is correct? What is the alternative name for the standard electrode potentials? Remember that the list that we have in the data booklet is the list of the standard reduction potentials. So it is given the name standard reduction potentials. Now, what is the order of standard electrode potentials? Well, we said we start on top from the most negative to the most positive. So we said the one on top is better reducing agent, tends to lose electrons. So it is at the top, the zinc loses electrons. And the one down is the most likely to gain electrons, or the better oxidizing agent. Again, this equation, what is its cell diagram? Well, let us take a look again. We have vanadium 2 plus going to vanadium 3 plus. That is a mixture of ions or solutions. So I need a platinum electrode. So my answer is C or D. Then we have the two lines which indicate the salt bridge. Now, what is happening in the other half cell? Copper 2 plus going to copper solid. So this involves a solid. And that means my electrode in that half cell is the solid, the copper, not platinum. We use platinum if we have only solutions. But if one of the reactants or products involves a solid, then that is my electrode. In a chemical reaction, the E cell is directly proportional to what? Again, I'm going to remind you, we said the E cell is directly proportional to delta S total. Again, this persulfate ions react slowly with iodide. And we said we use a catalyst of iron 2 or iron 3 to the mixture. Which of these is the most likely reason why this reaction originally is slow? We said this reaction originally is slow without a catalyst. And when we use a catalyst, we use the iron 2 or iron 3 to be a catalyst. Why is it slow? Remember that if something is slow, probably out of these choices, then the activation energy is high. If we don't have that choice, then we say because both reactants are negatively charged, so originally they will repel. They will not like to come together and collide and react. So that is why they need a catalyst. And that is actually why the activation energy is high. The cell diagram now is given. What are the half equations? So if he gives me the cell diagram and I want to deduce what are the half equations, obviously what is happening, remember that it is arranged according to what is happening. So iron 2 plus is changing to iron 3 plus. So that is my choice. So it is A or B. And then the Br2 is changing to 2Br minus. So remember that looking at it, well, this is what is happening according to the order in which it is written in the cell diagram. This question is about this reaction. The electrode potential for iron 3, iron 2 is plus 0.77. What is the electrode potential for titanium 2 plus titanium electrode system? I'm going to remind you again that when we're given electrode potentials, this is for the reduction. So, okay, I have reduction in there, so the E note is what he gives me. But then what is happening in my reaction is titanium solid to titanium 2 plus, and that is oxidation. So when we calculate the E that we calculated is actually for oxidation. So when I want to write it, I should write or I should provide electrode potential for the reduction. When we're asking for electrode potential, we're asking for the reduction. In my reaction here, the E comes out to be plus 1.63, that's okay, but that is for oxidation from titanium solid to titanium 2 plus. So the electrode potential for that system is minus 1.63. Please pay attention. Okay. What metals should be used for the electrodes in this cell? Well, we have iron 3 plus, iron 2 plus, a mixture of solutions, and we said that means I need a platinum electrode. So my answer is C or D. What about titanium 2 plus? We have titanium 2 plus titanium solid, then the electrode is the titanium solid. We're given a cell diagram, write the half equations for the two half cells, and hence the overall ionic equation for the reaction that occurs. So from what is written, I should be able to deduce. This is what I have in the data booklet. But in my reaction, what I have is the Mn2 plus going to MnO4 minus. Remember, the arrangement in the cell diagram is the arrangement in the actual equation. So I have to reverse that. So I reverse that. Now, the other part is the BiO3 minus changing to Bi3 plus. So I can deduce that this would be the BiO3 minus. You might not find it in the data booklet, but you should be able to determine if I want to change BiO3 minus to Bi3 plus. I should be able to write the ionic half equation. If you remember from writing half equations, if on the left I have oxygen, that means on the right I should have water, and that means I need to balance that on the left with H+. And then you balance and find that you will need 2 electrons to have equal charges before and after the arrow. So that is that second equation. Now I need to add them all up to get the overall ionic equation. Of course, in order to add them all up, I have to make the electrons equal. Now, how do I make the electrons equal? I can multiply the upper equation by 2 and the lower equation by 5. Can you see that? That would make each of the electrons 10. But remember that when you multiply something, you're multiplying all through the equation. So this is what we end with. And then we cancel whatever is the same before and after the arrow. So the 10 electrons will be cancelled. But I also have water before and after the arrow. So I cancel them and write what is left. I have H+ before and after the arrow. I cancel them and I write what is left. And the overall equation is just writing everything before the arrow and everything after the arrow. So that is my overall ionic equation. Please practice all of this. Try answering the question before I say the answer. An electrochemical cell is set up. A half cell is made from a piece of zinc and a solution of zinc chloride. A second half cell is made from a piece of metal G and a solution of its chloride. The 2 half cells are connected and a current allowed to pass for some time. Now, they found that the zinc electrode increased by mass and G decreased in mass. Now, what is G? Remember that the one that increased, that means this is the one where the more zinc was formed. And that means that G must be a metal that is more reactive than zinc, better reducing agent, so that it is the G that will lose electrons and become ions, so it will decrease in mass. So the one here that is more reactive, better reducing agent would be magnesium. Draw a label diagram of the apparatus. So you could have a question like this. Draw a label diagram of the apparatus you would use to measure the standard electrode potential of copper 2+ copper electrode with a standard hydrogen electrode. So we're trying to measure the standard electrode potential of the copper 2+. That means we're going to connect it to hydrogen electrode. You should know the hydrogen electrode should be at 298 Kelvin and 100 kilopascal. And it should have a platinum electrode dipped into a concentrated solution of sulfuric acid, 1 mole per decimeter cubed concentration, and wires going to the other half cell, that is the one where we have a copper electrode in copper ions of concentration 1 mole per decimeter cubed, and there is a salt bridge of potassium nitrate solution connecting the 2 half cells. Draw a label diagram of the apparatus used to measure the EMF of a cell with copper and zinc. So now I have the 2 half cells. One of them is copper in copper ions and the other one is zinc in zinc ions, and the solutions are connected with a salt bridge, which is also potassium nitrate solution, and the electrodes are connected with a wire in the external circuit. Okay, this question says the standard electrode potential for 2 half cells is shown. Explain in terms of electrode potentials why acidified dichromate ions react with concentrated HCl to form chlorine even though the overall E cell is minus 0.03 volts. So these equations that we have we have the chloride going to chlorine and the dichromate going to chromium 3+. Of course, we need the chloride to go to the chlorine, and that means the E of the cell is inverted. The sign is inverted, so the E of that cell is minus 1.36, and overall the E of the cell is a negative value. But the idea is it is a slightly negative value, so it's minus 0.03 volts. But if we use concentrated hydrochloric acid, it can become positive, and that is because if I add concentrated hydrochloric acid, then I am increasing the concentration of H+ ions, and that means the point of equilibrium in that first equation will shift to the right, so the value of E would increase, so the positive will be slightly more positive. Now the chloride to chlorine, we're adding concentrated HCl, so the concentration of the chloride ions would also increase. This will shift the point of equilibrium in that second equation to form more chlorine, and that means the E note for that equation will be less negative. It will increase, so instead of being minus a big number, now it's minus a smaller number, and that means that overall, when I add them up, the positive has increased and the minus has become less negative, and therefore the overall E cell, instead of 0.03, it would become positive and the reaction would be feasible. Write the cell diagram using conventional representation of half cells for the reaction to produce chlorine. So these were the equations. What is the cell diagram? We said we start on the left. Of course, we started with chloride to give chlorine. We start on the left with the oxidation. Where is the oxidation? That is the chloride to chlorine. These are solutions and a gas. Again, we don't have a solid in that half cell, so the electrode has to be platinum. So I start with platinum, and please don't forget the state symbols. And then I have a double line in the middle to indicate the salts bridge, and on the right we have the reduction part, so that is the Cr2O7 2 minus aqueous plus 14H plus aqueous. That's one part, and the other part is 2 chromium 3 plus 7 water. Again, this is a mixture of solutions or liquids. It's solutions, and that means I need also a platinum electrode. Are we okay with writing cell diagrams now? Okay. So then the next question here is talking about calomel electrodes. So mercury 1 chloride is known as calomel. A saturated calomel electrode may be used as an alternative to the standard hydrogen electrode. So this we use instead of the standard hydrogen electrode to determine the electrode potentials. The half equation for this electrode is given. The standard electrode potential of the calomel electrode is given as plus 0.24. Remember that the electrode potential for the hydrogen was given 0 volts. The calomel, it states, we did not study calomel, but we're told that the electrode potential is plus 0.24 volts, suggests why potassium chloride crystals are needed in the outer tube of the electrode. Can you see the setup of the electrode? A glass tube, mercury liquid, saturated. I want the solution there to be what? Saturated potassium chloride. So I keep potassium chloride crystals at the bottom to keep the solution saturated with chloride ions. Then a calomel electrode was used to measure the standard electrode potential. Notice that the calomel electrode is all one part. It's not something in a beaker with solutions and so on. So we're going to connect it directly in that one beaker to the tin electrode, and the reading on the voltmeter of this cell was plus 0.37. Deduce the standard electrode potential for the tin 2 plus tin half cell. Well, okay, this is the equation for the calomel electrode, and we have the E of the calomel is plus 0.24, and we are being told that the E of the cell overall is plus 0.37, and that means the standard electrode potential for the tin 2 plus is minus 0.13 volts. Write the overall equation. So if we have this, we have the calomel equation given, and the tin is tin 2 plus 2 electrons. The overall, both of them have the same number of electrons, so we just cancel them and we write what is left. So just one advantage of using a calomel electrode. We said this is the use of the calomel electrode. Now, one advantage in place of using a calomel electrode in place of a standard hydrogen electrode. So what advantage do we have using the calomel? Obviously, you can see that we did not need a salt bridge. We don't have two half cells. We have the calomel is one thing, and then we connect it directly to the other half cell, so we do not need a salt bridge. And that's the end of these questions. I hope this chapter is much better for you now. Thank you for listening, and please keep listening to the videos. Thank you.